Hello, my name is Stylianos Vassiliou, and I will be presenting leveraging control flow similarity to reduce branch predictor cold effects. Many companies have moved away from the monolithic architecture to microservices, using it to implement many different online applications such as e-commerce platforms. This makes such applications a collection of services that can be developed and scaled independently and communicate via the network. Microservices have a tight time constraints, and so each process needs to be a few microseconds, making them sensitive to added overheads. One such overhead is the cold effects. The cold effect overheads comes from three pipeline components: the instruction and data caches, which must fetch the process data, and the branch predictor, which needs to observe branches and learn their behavior. In large programs, this cost is amortized over time, but smaller ones don't get this chance. One reason for cold effects is process interleaving. To improve server utilization, providers overrun multiple microservices on the same core. However, this means that many other processes may run between two executions of the same process, causing interleaving. When a job runs for the first time, the system has no prior context, and so it starts cold, and the performance suffers as it warms up. If it runs again soon after, it benefits from the leftover state. But if other jobs run in between, then they can evict or override this state. So when the original job returns, it starts cold again. Microservice processes are small. Most processes are less than 100,000 dynamic instructions, and at the same time, the static instructions are a significant percentage of the dynamic ones. This means that it has no time to amortize the cold effect overhead, and when the query is executed once again, most of the branch targets learned won't have the opportunity to be used. We analyze the impact of cold effects on real hardware by measuring the cycles per instruction of different microservice processes, with lower values being better. We induced the cold effect by power getting the core between each query, flushing the processor state. For the warm execution, we run the query sequentially without power gating. As we see, flushing the state causes a significant slowdown. Finally, there is a vast difference between cold and warm prediction MPKI. Because the warm-up happens by running the queries without flushing the state, the improvement of the MPKI comes from having the state from those previous executions, suggesting that they have similar control flows. In this work, we evaluate the control flow similarity between any two queries of a given microservice. We implement the similarity-based predictor, a hardware-software co-designed predictor that captures the control flow of a representative reference query and reuses it to make predictions for new queries. Then we develop Chess, a more practical predictor that augments baseline history-based predictor with the similarity-based predictor and a static hint. And we show that Chess approaches the accuracy of a fully warmed-up predictor. The similarity-based predictor is a profile-guided predictor that has an offline analysis to find a representative trace, and the online predictor that uses the trace it found to dynamically predict branches. For the similarity-based predictor, our first step is to collect traces. To do this, we run many queries offline and use a trace collection tool to trace them. A program has its static code, and depending on the input, it can create different dynamic executions from that code that we capture. Here we see two possible traces for the program. One is used as the reference trace, and the other the execution trace. We want to evaluate how similar the execution trace is to the reference trace used. The two traces start the same, so we say that they are convergent. In the fifth instruction, they take different paths and become divergent. In order to find where they will become convergent again or reconverge, we have to find their convergence address. To find the convergence address, we use the control flow graph, which is a which is a representation of the static code. In this, each node or basic block is a straight line sequence of instructions with a single entry and exit point. Edges show the possible paths the program can take between blocks. Control flow graphs have a useful feature, the immediate post dominator or reconvergence address. That is the first address that a block will always arrive at, no matter the path it takes. For example, block 3, whether we go to block 5 or block 9, will always arrive at block 15, making it the immediate post dominator of block 3. Similarly, we determine the reconvergence address for all blocks. This is essential for ensuring correct control flow when handling divergence and resuming at the nearest possible reconvergence point. To find this information and add it to the traces, we use the similarity-based predictors reconvergence analysis. As noted, the two traces diverge at the 5th instruction. The reference then looks up at the reconvergence address we identified and locates it in its own trace, monitoring for when the execution trace reaches that point. In the meantime, the execution trace continues without the reference trace until it arrives at the address the reference trace is monitoring. Afterwards, the two traces are convergent again and continue together. From this analysis, we take two metrics for the execution trace: coverage, the ratio of convergent branches relative to the total number of branches, and accuracy, the ratio of branches with correct prediction relative to the total number of convergent branches in the execution trace. The final step of the offline analysis of the predictor is to choose the reference trace. To do this, we compared all traces with all others and chose the one that, when used as a reference, gave us the highest average coverage. For our experiments, we divided the trace to train and test sets. We analyzed 10 different processes and used the chosen reference trace from the training set for each process. We saw that the coverage for most processes was above 90%, supporting our initial theory that they have high control flow similarity. When we compared the accuracy of the control flow similarity with a baseline predictor fetch for the covered part of the execution, usually the similarity is near 99%, while the fetch predictor is usually below 85%, further showing the high control flow similarity across queries. To give the predictors for the similarity-based to give predictions, the similarity-based predictor uses the selected reference trace with the reconvergence points alongside a baseline fetch predictor. It follows a policy that relies on similarity predictions when traces align using the reference trace and falls back to the baseline predictor upon divergence, handling the branches not covered by the reference trace. When we compared the MPKI between a cold fetch predictor and the similarity-based predictor, we saw that it significantly decreased the MPKI of the cold fetch predictor. Unfortunately, this approach needs a big reference trace of more than 10,000 instructions, meaning that it will have a big overhead in load time and cost in saving it. That is why we suggest chess, an expansion of the similarity-based predictor designed to reduce the trace length without losing the high accuracy of the similarity-based predictor. Chess achieves this by finding branches that can be predicted correctly by other predictors and delegating and removing them from the trace. This way, we will only keep branches that will benefit from using the similarity-based predictor. The first category that can be removed is indirect branches. By waiting until the decode stage, their targets will be known. We can also remove the return branches because RAS is very accurate even when code. Here we see the control flow graph with the reference trace on the top right, and the arrows in the trace point to the reconvergence addresses. From here, we will start removing entries. We want to remove direct and return branches here, but we must maintain the correct and effective control flow in the reference trace. This requires cautions with instructions whose reconvergence addresses point to the entries we are removing. In these cases, it is safe to redirect the convergence to the removed branches target, since these direct branches have only one path and never diverge. For example, here, any instructions originally pointing to address 16, when we remove address 16, will be redirected to address 2. We can further classify conditional and indirect branches offline using a 2-bit encoding in order to delegate them to other predictors. If a branch has heavy bias to taken or not taken path, then we mark them as easy to predict and predict them directly with the hint bits using the target we will find at from the decoder. If the call fetch predictor is sufficient, we also mark them as easy to predict to use the fetch predictor. Finally, the rest are seen as hard to predict and use the similarity-based predictor. Now, we only have to remove those branches marked as easy to predict. To achieve that, we follow the same process we did for the direct branches. This approach alters the behavior of the reference trace, affecting its correctness and effectiveness, especially when a branch determines whether execution follows a path with easy or hard to predict instructions. For example, block 4 that we previously removed introduces ambiguity. After predicting branch 2, we no longer know which path the execution will take at block 4. As a result, we can't tell whether the next hard to predict instruction is block 10 or block 2, making the reference trace unreliable. This forces us to become conservative and diverge at block 2, potentially missing opportunities to predict some hard to predict branches. To solve this, we found the cases that would cause this problem and kept those easy to predict instructions necessary to not lose any hard to predict. The solution is to keep any easy to predict branches that follows this condition. If between an easy to predict instruction and its reconvergence point exists a hard to predict, then we keep that easy to predict and will be referred as retained easy to predict instruction. As we mentioned before, chess needs to wait until the decode stage. As such, we are going to attach chess to a normal pipeline like so. If the prediction it gives is different from the prediction of the fetch predictor, it will override that prediction and do a mini flash of the front end. Chess has a multiplexer to determine the predictor it will use, that uses the static hint we found offline coming from the decoder. For the similarity prediction, it has another multiplexer that remembers if it is convergent or divergent. If it is convergent, it takes the predictions from a trace buffer, and if it is divergent, it uses the fetch prediction. Compared to the original size, removing the direct and return branches had a substantial improvement, but it was still very big. Removing all the easy to predict, on the other hand, brought us to manageable levels, and when we reintroduced the retained easy to predict branches, the increase was small, achieving chess' goal of reducing the trace length. At the same time, when we had a reference trace with only the hard to predict branches, we noticed a substantial increase in MPKI compared to having the entire trace, while reintroducing the retained easy to predict in the reference brought the accuracy back to the levels of having the full trace. We evaluated performance on ChampSim, with 1 being the performance of the warm fetch predictor. The cold fetch had a nearly 40% increase in execution time compared to the warm predictor, while a cold fetch predictor with a warm bimodal showed only a 15% increase, and using chess reduced it to just a 5% increase. Additional results are available in the paper, including comparisons with state-of-the-art predictors like Whisper. In this work, we showed that it is hard for cold history-based predictors to be accurate. We introduced a new predictor component, the similarity-based predictor, which leverages control flow similarity from past executions. We implemented chess, a predictor with that combines the similarity-based predictor with static hints. and then default history-based predictor. And finally, we demonstrated that chess improves performance and MPKI using only a small reference trace. Thank you for your attention. I am open to any questions.